You have a sorted list of 1 million names. You need to find one specific name. A beginner scans from the first entry and checks each one in turn. In the worst case, that is 1 million comparisons. A developer who understands binary search finds that same name in at most 20 comparisons. This video explains exactly what binary search is doing at each step, why it achieves that dramatic reduction, and what you need to know to implement it correctly and use it effectively in real systems. Binary search is an algorithm that exploits a single property of a list that linear search ignores entirely: the fact that the list is sorted. If you know the list is sorted, a single comparison against any element tells you not just whether that element is your target, but whether your target is somewhere to the left of it or somewhere to the right of it. You can rule out enormous portions of the list in one operation. Binary search does exactly that again and again until only one candidate remains. The most intuitive way to understand what binary search is doing is through the classic guessing game. I am thinking of a number between 1 and 1000. If you guess 500 and I say higher, you have eliminated 500. Every number from 1 to 499 is off the table, and so is 500 itself. Your next guess is not 501, it is 750. You are always targeting the midpoint of the remaining candidates. Every correct guess cuts the remaining search space in half, regardless of how large it started. Binary search applies this exact idea to a sorted array. You begin with the entire array in scope from index 0 to the last index. You find the element at the midpoint of that range. You compare your target value against that middle element. If the target matches, you are done. If the target is less than the middle element, the answer must live in the left half of the current range because the array is sorted and everything to the right is at least as large as the middle. If the target is greater, the answer must live in the right half. You have now eliminated half the array with exactly one comparison. You repeat the same process on whichever half remains. Find the middle of that half, compare, discard the half that cannot contain the target. The search space shrinks with every step, from 1 million elements to 500,000 to 250,000 to 125,000 and so on. After just 10 steps, you are down to under 1,000 candidates. After 20 steps, you have fewer than 2. That is why 1 million entries requires at most 20 comparisons and why 1 billion entries requires at most 30. The formal name for this rate of shrinkage is logarithmic time complexity. Computer scientists write it O of log n, where n is the number of elements and the base of the logarithm is 2. Log base 2 of 1 million is roughly 20. Log base 2 of 1 billion is roughly 30. The number of comparisons grows almost invisibly compared to the growth of the input. Linear search is O of n, double the data, double the comparisons. Binary search is O of log n, double the data, add one comparison. This is one of the most important practical differences in algorithm design. Binary search has two hard requirements. The first is that the collection must be sorted. This is non-negotiable. If elements are in random order, then seeing the middle value tells you nothing about which side your target is on. Smaller values and larger values are scattered randomly on both sides, and you cannot safely discard either half. The second requirement is random access. You need to be able to jump to any index in the array in constant time. Standard arrays and array backlists provide this. Linked lists do not. Reaching the midpoint of a linked list requires traversing from the head one node at a time, which defeats the performance benefit entirely. The implementation follows directly from the logic. You maintain a left pointer and a right pointer, initialized to the first and last valid indices. On each iteration, you compute the midpoint as left plus right divided by 2, using integer division. You compare the array element at that midpoint to your target. If they match, you return the midpoint index immediately. If the target is less than the element at midpoint, you move the right pointer to midpoint -1, cutting off the right half. If the target is greater, you move the left pointer to midpoint +1, cutting off the left half. The loop continues until left exceeds right, at which point the target is not in the array and you return a sentinel value such as -1. There is a subtle bug in the midpoint calculation that has caused real problems in production software. Writing the midpoint as left plus right divided by 2 can produce an integer overflow when left and right are both close to the maximum value of a signed integer, which is possible when searching very large arrays in a language that uses fixed-width integers. The safe alternative is to write midpoint as left plus the quantity right minus left divided by 2. This is mathematically identical but cannot overflow because right minus left is always a non-negative number smaller than the full integer range. Get into the habit of writing it the safe way. Binary search does not only exist as a standalone function. It is the foundation of a family of standard library tools and data structures you encounter regularly. In C++, lower bound and upper bound use binary search to find the first position where a value is no less than the target, and the first position where a value is strictly greater than the target, respectively. In Python, the bisect module provides bisect left and bisect right for the same purposes. These functions let you find insertion points in sorted lists, count occurrences of a value, and implement sorted multisets efficiently, all in O of log n time. Database engines rely on binary search constantly. A B-tree index, which is the default index type in most relational databases, is organized so that a binary search can locate the desired leaf page from the root in O of log n page reads. The index is essentially a sorted structure, and the database traverses it using the same divide and discard logic. Searching a table with 10 million rows via full scan can require 10 million disk reads in the worst case. Searching it via B-tree index typically requires 3 or 4. The difference in real-world query latency is often 2 to 3 orders of magnitude. Git bisect is another practical application. When you know a bug was introduced somewhere in a sequence of commits but you do not know which one, Git bisect applies binary search across the commit history. It checks out the midpoint commit, you run your tests, and you tell Git whether the bug is present or absent. Git halves the search space with each answer. A history of 1,000 commits is bisected in 10 steps. This is one of the most powerful debugging tools available in any version control system, and it works entirely because a sequence of commits ordered by time is a sorted structure. Knowing when not to use binary search is as important as knowing when to use it. Binary search is only faster than linear search when you perform multiple searches on the same dataset. If you need to search a collection once and it is not already sorted, sorting it costs O of n log n comparisons, which is worse than a single O of n linear scan. Binary search earns its advantage when the sorting cost is paid once and amortized across many queries. If your data arrives pre-sorted, or if you maintain a sorted structure as you insert, binary search is the right tool immediately. If you are doing a one-off membership test on an unsorted list with fewer than a few hundred elements, linear search is simpler and fast enough. Binary search has 3 common variants, and confusing them is the most frequent source of bugs. The first variant finds any index where the target exists and is sufficient when you only need to know whether the target is present. Second variant, the lower bound, finds the leftmost index where the target exists or where it would be inserted to maintain sorted order. The third variant, the upper bound, finds the rightmost such position. Each variant adjusts its boundary updates and return value differently. The boundary condition errors that affect these variants have appeared in textbooks, in standard library implementations, and in widely deployed production systems. The discipline that prevents them is to choose your interval definition, either closed on both ends or half open, before writing a single line of code, and then enforce that definition consistently at every boundary update throughout the function. 5 test cases that catch nearly every binary search bug are: an empty input array, a single element array where the target is that element, a single element array where the target is absent, a target located at the very first index, and a target located at the very last index. These boundary conditions exercise every branch in a correct implementation and expose every off-by-one error in a flawed one. Make these your standard test suite whenever you implement binary search from scratch. That is binary search. Thanks for watching.